Welcome to our channel, where we explore the transformative power of emerging technologies. In today's video, we'll examine the rise of smart grids and how the Internet of Things is revolutionizing energy efficiency. As the world battles climate change and rising energy demands, smart grid technology is emerging as a critical solution. 1. What is a smart grid? A smart grid refers to an electricity network equipped with sensors, communication links, and automation. It enables two-way communication between utilities and consumers. IoT devices, such as smart meters, grid sensors, and intelligent controllers, are the backbone of smart grid architecture. 2. Why energy efficiency matters. Electricity production accounts for a large share of global greenhouse gas emissions. Energy waste and grid instability contribute to dated infrastructure costs and higher consumer bills. Improving energy efficiency is essential to decarbonize power systems. 3. IoT components in a smart grid. Key IoT devices include smart meters at homes and businesses. Sensors on distribution network switches and transformers monitor temperature, load, and fault conditions. Phasor measurement units offer real-time snapshots of grid stability. 4. Two-way communication and data flow. Smart grids depend on continuous data exchange. Meters send consumption data to utilities, while control commands are sent back. This feedback allows demand response programs like peak pricing. Utilities can identify outages or overload risks as they occur, rather than after the fact. Point 5. Demand response and load shifting. Demand response involves adjusting electricity usage based on grid conditions. When demand spikes, utilities send signals to smart devices, such as thermostats or water heaters. 6. Integration of renewable energy. Renewable sources like solar and wind are variable in output. Smart grids use IoT-enabled inverters and sensors to predict generation and balance load dynamically. Excess solar energy can be stored in batteries or sent back to the grid. 7. Real-world smart grid projects. Europe has deployed several smart grid pilots powered by IoT. In Denmark, smart meters and in-home displays let consumers optimize energy use. Germany's virtual power plants aggregate small generators and demand-side devices. 8. Real-world smart grid projects. North American utilities are integrating IoT into smart grid infrastructure. California's smart grid network uses sensors across power lines and substations to anticipate faults. Ontario's smart meter rollout allows customers to enable dynamic pricing. 9. Real-world smart grid projects. Asia and Middle East. Smart grid pilots with IoT are emerging in Asia and the Middle East. In Singapore, a city-wide energy management system monitors buildings and district cooling. 10. Benefits for utilities and grid operators. 11. Consumer benefits. Residential and commercial customers gain from smart grids as well. Energy usage is displayed in near real-time on dashboards or apps. This empowers consumers to reduce bills and improve carbon footprints. 12. Cybersecurity and data privacy. With so many connected devices, security is essential. Smart meters and grid sensors create access points for cyber threats. Utilities must encrypt communication, isolate IoT segments, and use authentication. 13. Standards and interoperability. Smart grid IoT systems need common standards to work together. Standards include IEEE 2030.5, IEC 61850, DLMS, COSEM for meters. Without these, devices from different vendors may not communicate. Interoperability ensures longevity and flexibility of smart grid installations. Many governments mandate these standards for smart grid rollout. 14. Network and connectivity challenges. Smart grids rely on reliable network coverage. Cellular, NB-IoT, LTE-M, LoRaWAN, or private mesh networks may be used. Rural and remote areas need wide coverage solutions. Urban regions require high-density support. 15. Edge computing and analytics. IoT devices produce a massive amount of data. Edge computing processes data locally at substation or gateway level. This reduces latency and bandwidth. Edge analytics detects anomalies and responds quickly. 16. AI and predictive maintenance. Events like wire faults or transformer degradation can be predicted by AI. Using sensor data over time, AI models identify patterns preceding failure. Maintenance can then be scheduled proactively. 17. Microgrids and community energy systems. Smart microgrids use IoT to manage localized energy systems. They connect solar panels, batteries, EV charging, and building loads. These islands can disconnect from the main grid during peak generation or emergencies. 18. Electric vehicles and grid interaction. EVs can be both energy demand and supply resources. Smart charging schedules vehicle charging times based on grid demand. Vehicle-to-grid technologies allow EVs to return power during peak events. IoT is used to coordinate charging stations, energy flows, and pricing. 19. Energy trading and peer-to-peer markets. Smart grids enable peer-to-peer energy trading. Households with solar and storage can sell surplus to neighbors. Blockchain or IoT-enabled platforms facilitate real-time tracking of energy flows. Thank you for watching this comprehensive overview of smart grids and energy efficiency powered by IoT. Leave a comment sharing which smart grid innovation you find most exciting. Thank you for watching, and we look forward to exploring the technologies shaping our world in the next video.